Welcome to the lecture of formal models. Today we will continue with the topic of bounded model checking, which we already started to discuss last week, and then we will proceed with a new topic which is closely related and which can be seen as some kind of predecessor of bounded model checking. Namely, we'll talk about planning, which can also be solved by using SAT solvers. But let's first quickly recapitulate what we discussed last week. So last week we introduced model checking in general as a technique to verify the correctness of software and hardware. The requirements that a system should meet could be, for example, formulated in a formal language like temporal logic, and then we have a model of the implementation that describes the realization of the system, and we want to know if the implementation is conformant to the requirements. And in model checking we simply have these two artifacts, give it to a model checker, and if everything is fine, then the model checker says there is no problem, and hence we can conclude that the software is verified and that the requirements of the specification are met on all possible execution paths. In case that there is a problem, the model checker returns an error trace, so it gives us a sequence of actions or a sequence of states in the execution of the system that result into a problematic state. And this is extremely useful for debugging. We quickly discussed that there are two kinds of model checking, roughly speaking. One is explicit state model checking, where the state space is explicitly traversed, and this has a problem with the number of states. So when you think about even about a small program, there are quite many states, and it requires very sophisticated techniques to deal with this huge amount of states. But there are such techniques. On the other hand, and this is the technique we considered in more detail, there is symbolic model checking, which uses logic to represent the model checking problem. The logics are, for example, propositional logic or QBF, which is an extension of propositional logic, and then the formula is given to a solver, and then without any manual intervention, the result is obtained. And we discussed how a model checking problem can be encoded into propositional logic. There are different kinds of properties that could be checked via model checking, and we considered safety, checking or ensuring that something bad will never happen. And today we will consider another property that we will see soon. We had this running example, which we will later use again. We have two processes, P and Q, which share a resource, and here in this Kripke structure we see how the transitions from one state to another state takes place, and the critical state is state D, where P and Q access the same resources. And the question is, when we check safety, is there an execution path such that state D can be reached so that we finally that we can show that the formula finally P and Q holds for some execution trace. Okay, so we want to know if there exists such a path. And we then discussed how the bounded model checking problem can be encoded into propositional logic. We have seen a construction where we say if we're in state A, for example, then we can go to state C, or we can go to state B. If we're in state B, we can go to A or to D, and so on. This was one approach. We have seen how to encode this into the limbal format, and then can use the stat-solver limbal to check the outcome. We have seen an alternative encoding which could become more compact, where we use a truth table. This is similar to the encoding we have used for translating circuits into Kripke structures or I/O automata. So we build a truth table and translate this truth table into a Boolean formula. We also discussed how to translate this into limbal format. Then we also said that this gives us one step in the system, and in order to do multiple steps, we have to copy this encoding of the transition relation. This we did. We saw how to do 2 steps in our example. We saw how to do 3 steps in our example, and then we continued with checking a safety property. So is there a path of length k to a bad state S, such that in S the property P is violated? Is there a path where globally P does not hold in K? And an important observation we made is that if this property does not hold, there is a finite counterexample, and this counterexample we want to have. And the important thing in bounded model checking is that we do not consider paths as arbitrary length, but we restrict the length to a certain constant, and this is necessary in order to know the number of copies of the encoding of the transition relation that are included in the propositional formula. And if the obtained formula is true, then the model gives us the counterexample. If the formula is false, then we need to increase the number of steps and see if we find a problem with an additional step. And this we will later in this lecture we will see a criterion how to choose the k. And then we had all components we need to in order to encode a bounded model checking problem in propositional logic. We had the encoding of the initial state, we had the parts of the formula that encode the steps, and we finally have the bad state that we want to check if it's reachable. Now I would like to show you how another property is checked with bounded model checking as a SAT encoding, and this property is called liveness. In liveness checking, we ask if something good property P will eventually happen on every path. So in other words, if the formula Fp is true for a Kripke structure. Now let's think a bit what it means that formula Fp is violated. Assume we are checking Fp for a Kripke structure K, then Fp is violated if we find a path in the Kripke structure that starts from an initial state, and on this path not P holds forever. This means we find an infinite path where P never becomes true. And this leads us to the following 2 observations, which are crucial for doing the encoding in SAT. First of all, if finally P does not hold in the Kripke structure, then this is different than in the safety case where we had a finite counterexample. So where we had the problematic case that if we reach the bad state after a couple of steps, now if Fp P does not hold, that means that we have an infinite counterexample, because this property P does never hold on the infinite path, and therefore the counterexample is infinite. Okay, this looks not so good, but we are lucky in the sense that the Kripke structure has only a finite amount of state and a finite amount of transitions. And this leads us to observation 2, namely that if the counterexample is infinite, then this has to be because of a cycle. And this means in order to detect if a liveness property is violated, what we need to do is we have to consider all the cycles in a Kripke structure and check if on one of these cycles property P does never hold. And again, we do a bounded approach, meaning that we restrict the numbers of state, or we fix the numbers of state and incrementally increase it. Okay, so how does this look in a SAT encoding? As before, we have the initial states, and again we use the encoding of the transition relation, and first of all we put k copies of the transition relation encoding into the propositional formula, such that we encode a path of length k starting from the initial state. Yeah, so we have this green part here saying we start in the initial state, and this first conjunction says that we are doing k steps. We start in S0 and go to state Sk. Okay, and now we realize the cycle check. This is this big disjunction we have here, and what we simply do is we ask if from state Sk it is possible to reach a state in one step which we have already visited before. Yeah, so the I is a running variable that takes values 0 to k. These are then exactly the indices of those states we have visited before, and we ask, can we go in one step from Sk to S0? Can we go in one step from Sk to S1, and so on, until we finally ask, can we go in one step from Sk to Sk, because there could also be a self loop. Yeah, and with this we check if there is a cycle. Only if there is a cycle, the part of the propositional formula which we discussed is true. And what we now have to include is the property which we want to check. This one is missing, and we have now here this big conjunction, and this big conjunction checks for each state which we are visiting if not P holds in the visited states. Yeah, so what we have is the initial state, the path of length k, then a backlink to an already visited state, and a check if not P holds in every state. And that's already the encoding of the liveness checking. Let's have a look at our example. Here we want to know if FQ holds for the Kripke structure, so if it's always the case on every path that Q gets access to the resource. And when we look at the Kripke structure, then we see that there is a path from A to B and from B to A, which is an infinite path, where Q is never granted access to the resource. Yeah? And this one we want to find. And here we do one step forward, and then we have to check if after this one step we are having a cycle that could be problematic. And yeah, here we use the transition relation from encoding from the last time, and in the yellow I have the one step we do forward. Note that this is not a static encoding going from A to B, but this could also be a step from A to C, or any other step that is possible. But by using this two, or by adding these two unit literals on the top level, we ensure that we start from A. Yeah, so we do one step from A. This is the first two lines we have here of the encoding. Yeah, and then we have to check for a cycle. And since we did one step, we visited two states. We visited the first state and the next state, and therefore we have to check if we can go back from the second state to the first state, or if we can go from the second state to itself. This is the gray part here. So the red part asks if we can go from the step we reached, from the state we reached after one step, if we can go back to the original state. And the gray, this is the red part, and the gray part asks if there is a self loop in the state that we reached after one step. Yeah, and finally we have to include the property check, and this property check asks if not P holds in the initial state, and if not Q holds in the initial state, and if not Q holds in the state we have visited after one step. Obviously, bounded model checking is incomplete if we choose the K too small, and the question is, what is a good choice? So is there a number which might be too large that we do unnecessary work, or how could we choose the K? And here there is the diameter of the Kripke structure that gives us an indication how we have to choose the maximal K for safety checking. And what is the diameter? This is the smallest number D for a given Kripke structure, such that for every path of connecting a state S0 to and a state SD plus 1 in D plus 1 steps, there is a path T0 to TL such that L is smaller or equal to D, T0 is equal to S0, and TL is equal to SD plus 1. What does this mean? If a state S is reachable from a state T, then there is a path of length D or less, such that we can go from S to T. Yeah. So the diameter gives us the longest, shortest path in the graph that a Kripke structure basically is, and this number indicates what is the maximum of required steps in order to ensure that we do not miss a problematic state. And yeah, this is a good estimation. The only problem is that computing the diameter of a Kripke structure is difficult. It's a difficult problem itself. For this, we even have to solve a QBF formula. Yeah, and for liveness, we have the recurrence diameter, which is the smallest number d, such that for every path S0, S1, and so on to SD plus 1, we find an index which is smaller or equal to d, such that the state SD plus 1 has been visited before. Yeah, so this is the maximum length of a non-looping path in a Kripke structure. And this can be formulated as a validity checking problem, but this means this is also a QMP hard problem which has to be solved in order to identify a reasonable choice. Yeah, but in principle it's possible to prove that bounded model checking to prove that if bounded model checking has been applied, that no problem has been overlooked. Otherwise, if this proof is not done, BMC is incomplete, meaning that if the k is too small and all checked formulas are unsat, then this does not give really a good insight. We shortly discussed how to choose the case, when to stop increasing it. But this has to be decided based on the application. In practice, BMC is very efficient because of the restriction of the path length, and what is extremely valuable is that on the one hand BMC is completely automatic, and on the other hand it provides the error trace in case of a problem. And what I've showed you is just the very basic ideas, and there are many tuning and pruning techniques to make it work in practice. So usually a lot of effort is put into rewriting the formula in such a way that it's easier to solve. This can be done by taking specifics of a problem into account, by sharing similar parts of the formula if there is knowledge about the structure. But many optimizations can also done directly by the SAT solvers, and we have very, very good techniques that help to solve even large formulas. Yeah, and with this I would like to conclude the discussion on bounded model checking and continue with planning. Propositional logic not only plays a crucial role in formal verification, so for checking if a software or hardware system is correct, but also in the context of artificial intelligence. And a very old topic that is of high relevance in the context of AI is planning, and in the following I will explain you how a basic variant of a planning problem can be solved with propositional logic. And in fact this is somehow related to the encoding of the bounded model checking, but in context to bounded model checking we did not deal with actions, but just with the execution of programs which were modeled by Kripke structures. But now we have really actions that should be considered, and what we want to do is we have an initial state and a goal state which we want to reach from the initial state, and we have a set of actions which we can execute in order to reach our goal. And we have to find a sequence of actions that lead us to the given goal. And as I said, this is one of the classic problems in AI, and it has many applications in many fields, in logistics. So when you want to schedule a good route for a package deliverer, for example, or for bringing the goods to a supermarket. Yeah, these are typically planning problems, and they in fact are very hard to solve. Then in robotics, you have a robot in some restricted world, and the robot should solve a problem or go to a certain position, and there are certain actions that a robot can perform, and this can also be encoded as a planning problem. Or you want to solve a task in a computer game. For example, you have to find some treasure, and for this you have to solve. You have to traverse the world, and there are some obstacles to be overcome. And yeah, this problem solving can also be encoded as a planning problem. In the following, I would like to discuss the following running example in order to illustrate how the concepts that we will introduce soon work. So we have a robot which we call R, and this robot operates in a world which is a 2x2 grid, as I have shown it here on the right. The green field is called field 1, the field above 1 is called 2, the blue field is called field 4, and the field below the blue field is called field 3. Yeah? And the robot R can do several things. First of all, it can move right and up in the fields 1, 2, 3. So if it moves up in field 1, it ends up in field 2. If it moves up in field 2, it returns again to field 1. Yeah, so this dashed arrow here indicates that it wraps around. And the same in field in all fields. Yeah, and if it moves right in field 1, it ends up in field 3. If it moves right in field 3, it ends up in field 1 again. And furthermore, R can lift its arm but it can only do this in field 3, so it cannot do it in field 1, 2, or 4, but only in field 3. And the initial state where robot R starts is field 1, and the arm is in position down. And the goal is to go to field 4 and have the arm up. So this is a very small example, just for illustration purposes, which you can immediately solve. So the robot will go from 1 to 3, lift the arm in field 3, and then go to the goal state. This would be a short solution of the problem. And yeah, but we will try to find this solution now fully automatically with SAT. And for this purpose, we define the components of a planning problem. And as you will see, it's quite similar to bounded model checking problem, with the difference that we have actions which update the state of the world. And now let's have a look what are the components of a planning problem. So first of all, we have a set of state variables. This is like in bounded model checking, in the Kripke structures, we have also Boolean variables which uniquely describe the different states. And the states itself are a subset of the power set of F. So we define a state S by the set of state variables that hold in a state, and the not included variables assumed to be false. Okay, this should not be so different to the things we have seen before. Maybe let's continue with the other easy things. So in the definition I have here, we have exactly one initial state, so this is an element of S, and we have several goal states, so G is a subset of S. So there can be only one goal state, but there can also be multiple. And now what's missing are the actions, and we define them in a set A. And one action is a pair consisting of a precondition and of an effect. A precondition is a subset of positive state variables and negative state variables, and this precondition tells us when action A is applicable. Yeah, so which of the state variables have to be true, which of the state variables have to be false, and state variables which are not mentioned here do not matter. Yeah, so not always all variables are relevant in order to execute an action. Therefore, we have to list the properties that should hold and the properties that should not hold explicitly. Yeah? And this means if a literal, now we have literals, we have variables or negated variables, and if a literal is not, if a variable is not mentioned either positively or negatively, then this means it is irrelevant for the action. And in the same way, we define the effect, and the effect gives us the result of an action. Yeah? So we update the state of the world. Either we set the positive literals and we set the positive literals to true, and the negative literals we have in the effect to false. Yeah? So this gives us the result of the actions, and again the variables which are not mentioned are not affected by the action under consideration. Here I have an example. In our robot world, the robot can be in field 1, 2, 3, or 4. Therefore, we have 4 Boolean variables. If R1 is true, the robot is at position 1. If R2 is true, the robot is at position 2, and so on. And we have the Boolean variable U, which tells us that R has its arm up, if it's true. Then for the actions, we have the lift action. Here we require that the robot is in field 3 and the arm is down as a precondition, and the postcondition is that after the execution of the action, the arm is up. Then we have the move actions. These in propositional logic, we have to define each move action separately for each field and direction, because we cannot parameterize these like we could do in predicate logic, where we would have arguments, but we have really to say if we want to move from field 1 to field 2, then the robot has to be in field 1, and this is the precondition, and the postcondition is that after the move it's not anymore in field 1, but it's in field 2. And similarly we can define it for the other move actions. Yeah? And what is now still missing is the initial state. We now say that in the initial state we have only one. The robot is in field R1, and we do not include the U here because the arm is down, and in the goal state here the U is missing. In the goal state is we are in state 4 and the arm is up. So here also U is missing. Yeah? This gives us the goal state. Okay, and now we have also to encode the transition from one state to another, and we assume that one action happens at one point in time. So when the robot does something, then one time element continues. And we use then a similar idea as in bounded model checking, that we encode the state transitions for one time point, for one action, and then have multiple copies in order to perform multiple actions over the time. And this we will do in the following. Before we now have a detailed look on how to encode the transition of states, let us first concisely define what is a bounded planning problem. And a bounded planning problem is simply a pair consisting of a planning problem P and a positive integer n, including 0, such that any solution for P of length n is a solution for Pn, and any solution of Pn is obviously a solution for P. Yeah? So in the bounded planning problem, we search for solutions of length n. And in order to now solve a planning problem, we can incrementally solve multiple bounded planning problems. We first set n to 0 and encode Pn as a propositional formula, and check if the propositional formula which we obtained is satisfiable. If it is satisfiable, then any of its models should encode a valid plan, and then we return this plan and stop searching for another solution to the planning problem. If phi is unsatisfiable, then this means there is no plan of length n. We increase n by 1 and continue at step 2, encode the problem again as a propositional formula and try to solve it. Yeah, and now in the following we will have a look how to do this encoding. So first of all, we have to identify what are the variables that occur in the propositional formula. And as we did it in the bounded model checking, we annotate the variables with a timestamp. Yeah? We have the current state variables, we have the next state variables, and similar, we have annotations also for the action variables indicating at which time point an action took place. So for example, if we have an action A, which is annotated by a 0, then it indicates that this action was executed at the very beginning. If it's annotated with a 3, for example, then this means this is the fourth action that was executed. Yeah, so we introduced this annotated variants for the state variables as well as for the action variables. We have for each time point we have an annotated version of the state variables, and a variable f v annotated with t is true if and only if v is true after t steps, so after executing t actions, it is true. And if we are in state Si after t steps, then the variables that are characterizing state Si are true with the respective time step. And similar, we have this annotation for the action variables. So action variable AT is true if action A is applied at step T. And the true action variables, which are part of a solution found by the SAT solver, are the solution of the planning problem. So if I have, for example, A0 true, B1 true, C2 true, then ABC is a sequence of actions that is a solution to the planning problem. We will soon consider this for the example, but before we do so, let's have a look how we define initial state and goal states. We said we have only one initial state, so we take the variables that occur in the initial state and require them to be true at time point 0, and those which do not occur in the set of state variables of the initial state, those are required to be false at time point 0. This is the initial state. And for the goal states, we have multiple ones. So we build this junction over the different goal states. So one of them has to be true. And and for one goal state, the encoding is similar as for the initial state. If we want to reach a goal state after n steps, then all variables that occur positively in the goal state are have to be true, and all variables that do not occur in the goal state have to be false at time point n. Now, how does this look for our example? In our example, we start with the robot being in field 1, so it's not in position 2, it's not at position 3, it's not at position 4, and the arm is down, therefore U has to be false. And for the goal state, we have to be in field 4, the arm has to be up, and the robot is not in field 1, 2, and 3. Yeah? So this is the encoding of the initial state and the goal state. And the important thing I forgot here is the annotation with the 0, or which I did not mention here, is the annotation with the 0 and the annotation with the time point where we end up in the state. And this will be fixed in the slides. Okay, and now let's proceed how to execute actions. And if we execute an action, then the current state of the world changes. Yeah? So if we execute action A at time point t, then at time point t, the preconditions of A have to hold. That is the first conjunction. And after the execution of t of A at time point t, at time point t plus 1, all the effects have to hold. Yeah, so all the literals which are here in the list of effects have to be true. And here we have the example. If we perform lift at time point 0, then the robot has to be in field 3 at time point 0, and the arm has to be down at time point 0, and in the next time point, at time point 1, the arm is up. If the robot is in field 1 and wants to perform a lift if the robot wants to lift the arm at time point 1, then it has to be in field R3 in field 3 at time point 1, and this is also a typo. The arm has to be down at time point 1, and it is up at time point 2. Yeah, and now let's have a look at a move. Assume the robot wants to move from field 1 to field 2 at time point 0. Then it has to be at field 1 at time point 0. And here is again a typo. At time point 1, it is not anymore in field 1, but at time point 1, it is in field 2, and so on. Yeah, this encodes how the robot performs actions. There are some side conditions which we have to consider in our planning problem. So first of all, two different actions cannot happen at the same time point, so we do not execute actions in parallel, and therefore for each action and for each time point we have to include a clause not A T or not B T. Yeah, so it cannot be that two actions are true at the same time point. For example, we cannot move from 1 to 2 and from 1 to 3 at the same time, at time point 0, or we cannot move from 1 to 2 and lift the arm at time point 0, and so on. Yeah, this we have to do for all combinations of actions. Yeah, this is also because of the expressiveness or the lack of further concepts in SAT that we have to do this enumeration that explicitly. And what also is important is that at each step we do at least one action. For this we build a big clause saying that at time point t we do action A1 or action A2 or and so on, or action k if we have k actions. For our robot, this means at time point 0 we move from 1 to 2, we move from 1 to 3, or we move from 2 to 1, or we move from 2 to 4, or we move from 3 to 1, or we move from 3 to 4, or we lift the arm. I hope I did not miss any possibility. Those are the actions, and the same we can do for time point 1. Yeah, and this is in principle the encoding of the actions and the transitions from one state to another with respect to a time point. And now there is only one thing that is missing, and this relates to properties that are not affected by an action, and these properties should not change. Yeah, because the SAT solver would think, okay, if we have a variable that holds at a time point t, then we have a new variable of a property that holds at t plus 1, and if there is no rule saying keep it the same, then it will change. And therefore we need rules that say keep untouched variables the same when other action or when an action is executed. And this we do with the so-called frame axioms, and these encode what changes by an action. And for every state variable, we have to add the following statement. If state variable p changes at step t or at time point t, then there must be an action A that is responsible for that change. And expressed in a formula, this looks as follows. If we have two cases, if p is true at time point t, but it's false at time point t plus 1, then this means that one action A has been executed such that not P is in the set of effects of A. Yeah? Only if P occurs in the effects of A, this means, and negatively occurs in the effects of A, this means it could change its state from true to false. And the same we do for the other direction. If P is false at time point t and becomes true at time point t plus 1, this means that one action has to be executed which has the positive P in the set of its effects. Yeah? Otherwise, it should not change. And this is really important in order to avoid some unintended modifications of the world. Yeah, for our example, this looks as follows. Here I have if U0 is U is false at time point 0 and true at time point 1, this means that the action lift was executed at time point 0. And now for the other case, if U is true at time point 0 and U is false at time point 1, then this should not be allowed. So this results in an invalid situation. So we say that this conjunction implies bottom, and if we eliminate the bottom, we get the formula not U0 or U1, meaning if the solver finds a solution where U is true up at time point 0, but it is down at time point 1, then in this case this clause becomes false, and therefore we encode the knowledge that a lifted arm cannot be put down again. Yeah, and here I have another example for a move operation, for a move action. This encodes the changes from or to field 1. If we are at time point 0 not in field 1, and if we are at time point 1 at field 1, then this means we have executed either the action move from field 2 to field 1, or we have executed the action free 1, both at time point 0. Yeah? And if we are if the robot is in field 1 at time point 0 and afterwards it's not anymore there, then it means execution the action move 1-2 has been executed, or the action move 1-3 has been executed at time point 0. Yeah, and this we have to do for all time points, for all steps, and for all of the state variables. And with this we now have the full encoding, and I would like to wrap up with putting it all together and show you how to implement the encoding in Limbol. I have prepared the encoding of the example we discussed so far in a text file. So I have collected here the definitions of the actions. So for example, if we do lift in the current state, then the robot has to be in the field 3 and the arm has to be down, and afterwards in the next time step the arm is up. So I did this for time point 0 and time point 1 here. Then I have the constraints indicating that at most one action can be done at the time point. Yeah, this is this list of binary clauses. Then what I have here is that at least one action has to happen. Here I have the 6 move actions and the lift action. And finally I have the frame axiom as we discussed them before. All of these elements are conjunctively combined. We can now store it and give it to limbool. We call limbool with the -s option in order to check satisfiability, and the file is called one step. And we get the solution. The lines where the right-hand side of the equality symbol contains a 1 means that the respective variable is set to true. In the lines with the 0, the respective variable is set to false. Now this looks a bit unexpected because here we are in field 3, in field 1, in field 1 we are also after one time step, and yeah, this is somehow weird because after one move or after one time step we should have left field 1. So what went wrong here? And what we have forgotten is to set the initial state. So we add the init state constraint saying that at time point 1 the robot is in field, at time point 0 the robot is in time point at time point 0 the robot is in field 1 and not in field 2 and not in field 3 and not in field 4, and the arm is not up, so it's down. This is the initial state. Now let's see what solution we get now. Okay, many more zeros and less ones. So we now have the situation that let's focus just on the 1. I just filter out those variables which have a 1. And okay, what is going on here? We are in field 1 in the beginning. We move from 1 to field 3. This is vacation 1. Then at time point 1 we are in field 3. This is okay, but what is strange here, R4 1 is 1 and R4 0 is 1. And now if we look how I did the initial state, then we see I made a typo and I put the 0 here, and I also forgot to put the 0 here, and now it looks good. And now we indeed get only those variables set which we are expecting to be set. So at time point 0 we are in field 1, then we make a move from 1 to 3, and afterwards at time point 1 we are in field 3, and R11 is obviously set to false. So we can also look again at the full solution, and here we have only 3 variables set to true, all others variables are set to false. Okay, this is good. Then let's have a look for 2 steps. Oh no, what I forgot is what if we want to ask if the goal state is reached after one action. So we have to set what is the goal state. We said we are in R4 at time point 1. So we want to ask if we are in the goal after one action, and up has to be true. And when we think about the solution we have just seen, then it's not surprising that this is unsatisfiable. Okay, so now about 2 steps. This I also prepared here. and I simply have the code from before. Here now the init state is already included. I have one copy of the definitions of the actions and the transitions, and if I want to execute a second action, I copy the whole code describing the actions and just replace the 0 by a 1. So the state 1 becomes the current state, and I introduce and I replace the 1 from before by a 2, so I get a new next state, and now I have time point 0, time point 1, time point 2, and can execute free action. This I do for all of the constraints I have, so the constraints duplicate, and I also have now a different goal state, which is U2 and R42. So it asks if after 2 steps are we in state 4, and is the arm up. So I have to now change the file, and this is again unsatisfiable as expected, because if we look here, after 2 steps we cannot reach the goal state. So now I have to get my Windows back. Here, and I also prepared a file with free actions, free steps. So here I added another copy where the current state is state number 2 and the next state is state number 3. And here I just realized I have a copy-paste error. I have to replace the y by underline 3 globally. So this was somehow lost, and now I have the here I also lost an x. Now I have the definitions of the actions, the constraints saying that at most one action can be done, and at least one action has to be done at time point 2, and also the frame axioms for saying that something does not change from time point 2 to time point 3, or what are the constraints to change from time point 2 to time point 3. And initial state as before, and now the goal state is U3 and R4 free. Okay, and now I can execute the 3 steps, and now the formula is satisfiable. I again filter the variables that are true, and let's see if this makes sense. At time point 0 we start in field 1, then we move from 1 to 3 and end up in, or let's put it into an editor that we see it's a bit better what is ongoing, so that we can sort it. At time point 1, at time point 0 we are in field 1, then we perform action 1 free, move 1 free, and go to field 3. So at time point 1 we are in field 3. Then at time point 1 we perform the next action, which is lift. This has the effect that at time point 2 the arm is up, and at time point 2 we are still in field 3. And at time point 2, we perform action move 3, 4. So we move to field 4. And this has the effect that the arm is still up. And at time point 3, we are in field 4. And therefore, we have reached our goal. And so the assignment is indeed a solution to our planning problem. So the solution to the planning problem is now the following. It's move 1, 3, lift, and move 3, 4, as we have expected. Yeah, and that's it. That's the way how planning with SAT works. So this is a very basic version I showed you. There are many examples where, for example, parallelism is taken into account, the collaboration between multiple agents, more complicated worlds, more complicated goals, and so on. But in principle, this is the core idea. What I have shown you, the important thing is that we have actions. The actions update the states of the world, and it's important that some things do not change by an action, and this we have to ensure by the frame axioms. Okay, and with this I conclude my discussion on planning, and thank you very much for your attention. Goodbye.